Okay, chapter 5.3, the Euclidean algorithm. So yeah, this is a very important thing in mathematics for sure. All right, let's take a look at what it says. So the Euclidean algorithm is based on the fact that if R is equal to A mod B, then the greatest common divisor of A and B is the same as the greatest common divisor of B and R. Okay. So let's go through an example here before we see the proof of this. Okay, so let's take a look at this. Okay, so here's the example. Since 105 mod 30 is 15, by this fact here, we see that the GCD of 105 and 30 is the same as the greatest common divisor of 30 and 15. Well, since 30 mod 15 is 0, right? We can see that the greatest common divisor of 30 and 15 is the same as the greatest common divisor of 15 and 0, right? So therefore, we see that the greatest common divisor is 15. Okay. So let's take a look at this theorem. And here's the theorem that we were using, right? If non-negative integer b is a positive integer, and if if r is equal to a mod b, then the greatest common divisor of a mod b, the greatest common divisor of a and b is the same as the greatest common divisor of b and r. And here's a proof of it. It's not that involved. It's just a matter of following through and using what we know from arithmetic, essentially, right? And then here's an algorithm, which I don't really want to get into. And so, but what I did want to show you is this next theorem, which is also very important for in mathematics. It's the fact that we can do this. This is going to look odd, but here we go. So if a and b are non-negative integers, not both 0, then there exists an s and a t such that the greatest common divisor of a and b is equal to s times a plus t times b. Okay, so all right, let's actually go through and take a look at this, an example of how we would actually find these numbers s and t. Okay, consider the Euclidean algorithm consider how the Euclidean algorithm computes the greatest common divisor of these two numbers, right? So we begin with a is 273, and we see that the remainder r equals what is it? 273 mod 110 is 53. Okay, so therefore we take 110 and 53, and we calculate what is 110 mod 53. And we see it's 4. And then you continue on in that way. What is 53 divided by 4? What is 53 mod 4 is 1, okay? And then if we set a equals 4 and b equals 1, the Euclidean algorithm next computes r is equal to, 4 mod 1, well, that's 0, okay? Since r is 0, the algorithm terminates, right, having found the greatest common divisor of 253 and 110 to be 1, okay? All right, so now let's see, how do we find this s and the t? Well, you go backwards, right? So here we have it. You start with this first equation that if you do the division up here as related to this fact, you see that we get that 1, so we write down 1 is equal to 53 minus 4 times 13, right? Because when you, that's how you get 1 is you take 53 divided by 4. It's, you can see that equation is true. Okay, then you can do the same thing. What do I mean by that? Well, now we know that 4 is 110 minus 53. So you plug that expression for 4 into the previous equation, and that's what you're seeing right here, right? And then again, you see that if you look at what 1 is equal to, 1, the greatest common divisor, is equal to, now we have 53. Well, you can see it right here, right? Well, we plug in, we know that 53 from this expression right here is what? It's 273 minus 110 times 2. So if you plug that in, notice now what you have is 1 is equal to everything in terms of some number times 273 minus or plus some other number times 110. Okay? And lo and behold, there we have it, that the two numbers we were looking for are 27 and negative 67. Okay. All right, so let me go. Yeah, okay, I just wanted to show you one more thing. Okay, so we did this calculation, right? And let's go down here and I'll show you where that calculation comes in to be very, very important because of this fact. Okay, computing an inverse modulo an integer, okay? That's what we're interested in. Suppose that we have two integers, n and n is greater than 0 and phi is greater than 1. Suppose that the greatest common divisor of n and phi is 1. Now we show how to effectively compute an integer s where s is between is less than phi, such that ns mod phi is equal to 1. So we call s the inverse of n mod phi. Okay, so you can do that. We noticed before what we just did in the algorithm. We can find an n. So we got this from this equation, right? We got a n times s mod phi is 1. But the problem is that we don't know that s prime is might be too large, right? So we need to convert s prime to a proper value by setting s equal to s prime mod phi. That guarantees that s is less than phi, and in fact s is not 0, right? And in fact, that's what we do. Now let me show you an example here. So going back to the one computation we did, remember we wrote down that 1 is equal to 27 times 53 minus, I think that's what we wrote down, minus 13 times 110. So what does that mean? Well, that means that, yeah, I guess that was one of the equations. Let's just assume this is correct. Well, that means that 27 times 53, right, is congruent, is equal to, that should be an equal sign, equal to that. Or in fact, 27 times 53 is congruent to 1 mod 110. So that would mean that 27 is the inverse of 53 mod 110. So that's something that we'll need to use in future sections. So, okay, thank you. Bye.